We've been talking about so much with vapor pressure and then vaporization. We also have a couple other phase transitions that we're going to talk about. These are some ones that you've probably seen before, but we're just going to review. Once again, vaporization, we know this is where we have liquid to gas, and the opposite of that is condensation. So we have melting, or you might have heard it called fusion, okay, delta fusion. This is where we have solid particles turning to liquid. Okay, so solid going to liquid, and the opposite of that is freezing, right? When our liquid is transforming to solid. Okay, and what I have over here, right, is how we're going to represent melting fusion, right? You just put that energy, delta H, fusion, F-U-S. Okay, we're going to talk about this in a little bit more. Okay, vaporization we know is delta H VAP, and then sublimation. Sublimation is where we have solid to gas, okay? Solid to gas. And then the opposite of that, when you're going from a gas directly to a solid, yeah, that does exist, right, is vapor deposition, okay? Vapor deposition. So, couple points you want to really pay attention to. So we talked about the transitions. So the temperature at which the solid and liquid phases of the given substance are in equilibrium, okay, is the points. That's the actual point. So you're going to have the melting point of a solid, right, when it's going from that solid to liquid. That's the melting point. Or you're going to have a freezing point of the liquid when it's going from that liquid to solid. And we could see a couple examples here. For example, right, if you got solid going to gas, okay, this is an example of sublimation. And now we understand, right, you got a gas going to solid, that's an example of vapor deposition. All right, so heating the curve. What we have here is water, and we're going to see a transition through its different phases. So we have our y-axis with our temperature and our x-axis with us adding heat over time, okay? So what we're going to see is we're going to start off as a solid. We're going to start off as a solid. We don't have no energy, and we're at a low temperature right now. So right now we're ice, right? Now over time we start to add heat or add energy, and we're going to reach our melting point. So once we reach our melting point, right, this is telling me at 0 degrees Celsius, this is my melting point for water. So this energy, right, that I just got here as we were adding energy is going to be used here, okay, to take that energy and convert that to this. Okay, so during this time, right, during this melting point, we're going to be at constant. Now, after we add this energy, guess what's going to happen, right? Melting point. So we're going from a solid to liquid. So bam, we've reached our liquid form here. So when we're a liquid for water, we're going to gradually continue to add that energy. And as we add energy, of course, notice we're increasing our temperature. So basically, when you increase temperature, you're adding energy. So as I increase my temperature, I'm adding my energy. I'm going to see, right, over time, I'm going to notice that, bam, right here, this is where I'm going to reach at 100 degrees Celsius, my boiling point, okay? So this is where, right, it's going to start to boil. And we're going to be, right, in this transition because we understand, right, that we need a certain amount of energy needed to transform those liquid molecules to gas molecules. So now, right, we reached a boiling point. Over time, that liquid, look at it, is getting energy, right? We're just giving, and it requires a lot of energy as we're noticing, right? Very different from this one, the ice. So we need a lot of energy, right, to turn this liquid into a gas. And this is what we're seeing here. That's why it's taking a long time. You know, it's like when you ever be trying to boil water, you be like, man, why is it taking forever? Well, we need all this energy to convert that liquid to gas. Till finally, right, after a little bit of time, all this energy that we've used here can go right into our gas transition phase. All right, so now we have our vapor here. And this is where we see the gas, right, molecules. Because after it got all that energy, it was able to now convert it to our gas molecules. So what do we see now with this heating curve? Okay, so now we got to see the math behind all of this. Okay, so what we're going to see here is, what does this look like, everybody? Specific heat, right? Specific heat. All right, we got our Q equals to our mass times our C, specific heat, times our change in T, right? That temperature change. Okay, so we're going to be using this equation to help us find this heating curve for water. Okay, so we broke this down into steps. It's broken down to steps, right? You got your, in step 1, right? This is step 1. The ice is warming up. Okay, so the ice is starting to warm up. Okay, and then we can see, right, with this ice warming up, this is the equation that we're going to have to use here. Okay, we'll get more into that in a little bit. Step 2, what did happen? Ice melting to liquid. Okay, so our ice, right, this is where we're getting that energy for it to actually start to melt to the liquid. So it doesn't take long, right, for the ice to be melted. 3, right, this is where our liquid started warming up, starting gaining that energy. Okay. And then 4, what do we see? This long step here is that the liquid water, okay, was vaporizing, right, to steam. Okay, so we can see, right, a lot of energy was required for that. 5, this is where now our steam will start to warm up. Okay, so now we're officially going to the next phase there, but we're going to stop here. Okay, so we can see, right, at the different points what's happening, right? A lot of energy to convert that to the gas, not as much energy down here. Now with this, we have these different equations. Okay, these different equations, like I said, think about specific heat. We're going to talk about each one of these equations right now. So let's talk about that step 1 with the ice warming. We were heating up 1 mole of ice at negative 25 degrees Celsius. Okay, up to the melting point, 0 degrees Celsius. So let's think about that equation. Specific heat, Q equals mass times specific heat capacity times delta T. So if we are heating just 1 mole of ice, that's 18 grams, right? Converting that 1 mole to 18 grams, right? Go to, if you're trying to remember how to do that, let's go ahead and hit that Chem 1 playlist. All right, dimensional analysis. Look at that one. All right, and the specific heat capacity. Now, notice, right, we have a different specific heat capacity, and that's because, right, this is ice. Okay, ice has a different specific heat capacity. So we're going to use 2.09. So we got our mass, 18 grams, times our specific heat capacity, 2.09. And the change in temperature. So how did the change in temp occur, right? We're going to see that we went from negative 25 degrees Celsius to 0, right? That's where we reached our melting point. Once we do this calculations, 18 times 2.09 times, in this case, positive 25, we're going to get 941 joules, or 0.941 kilojoules, okay? As our Q, or our energy, for our ice warming up. So it took 0.941 kilojoules for our ice to warm up. Let's go to the next step. This is when the ice was actually melting to the liquid. So when the ice was melting to a liquid, we're going to use a different equation here. Okay, in this case, we're going to use our N, and then we're going to times that, okay, by our delta H fusion, all right, our enthalpy of fusion. Okay, so the points are very simple. You're usually going to take the moles and multiply that by whatever process we have. So in this case, because we're going from the ice being melted to a liquid, we know that we need our enthalpy of fusion, okay, because we're going from solid to liquid here. Now, what we're going to see here is that we still got that 1 mole of ice, so it's still the same. 1 mole of ice, we're going to put 1 mole here, okay, so that's the key difference between this equation. We got moles times our whatever process, so moles times our 6.02. So this is enthalpy of fusion. It's given to us. It's given, so it's a given basically. And this is always going to be 6.02. So I'm going to multiply this, and what I'm going to see, right, is that my energy, right, when it was being melted to a liquid was 6.02 kilojoules. Okay. Now let's talk about when we got our liquid water and it's warming up, right? This is a process where it was gaining that energy about to being transformed to the gas. So once again, it's still the same amount. We still got the 1 mole of water, and at 0 degrees Celsius, we started adding energy, right, increasing the temperature till we got to 100 degrees Celsius, where it reaches boiling point. And now we're back to, because of this, using that Q equation, the specific heat equation, okay? So basically, everything is basically the same, okay? 1 mole of water hasn't changed, so that's going to be 18 grams, okay? Specific heat capacity, now this has changed. So before, right, we used 2.09. That's because of ice. However, right, for water, we have to use a different specific heat capacity, 4.18. Okay, so this is the one that's more common that probably people have seen, the 4.18. So we're going to use this one, right, for the liquid water. But understand, right, it's still all water. It's just we have different specific heat capacities for each one. Now, right, we got our change in temperature. We went from 0 to 100. So remember, right, anytime you got this delta T is final minus initial. Okay, so you don't want to do 0 minus 100. Your final temp was 100, right, minus your 0. That's what we saw in the other one too. Now, we do our math. We're going to see that we're going to get 7.52 kilojoules. Okay, we're going to get kilojoules. Keep it going. Fourth step, right, now we're going to points again. So with points, notice we're going to use a different equation, N times whatever the process is. So we got our 1 mole of water at the boiling point, so that 1 mole is still the same. But now, right, we got our enthalpy of our, in this case, that liquid water to steam. So basically at each point, the boiling point, right, it's going to be different. So we're going to see, right, that that's going to be 40.7. So Q times our 1 mole times our 40.7. Once again, this is given. It just depends on the process. Okay, so in this case, you want your boiling one. Okay, so that enthalpy is 40.7 for water. You multiply, and we're going to get our energy as 40.7 kilojoules. And then the last step with this thing that was warming. Okay, so this is that point step that I mentioned before. Okay, so notice, right, we got a different enthalpy, specific heat right here. So still 1 mole. That's still going to be the same. And now, right, it's steamed up from 100 to 125. Okay. So now, right, since it's on that other step, warming, we're going to take everything and apply it all again. 18 grams mass, still because it's still 1 mole. Now we're in the gas state, so now we've got a different specific heat, 2.01. And then notice the final minus initial, 125 minus 100. And we do our math here, we're going to see that that energy required for that process was 0.904 kilojoules. Okay.